Once again, great souls, and welcome to yet another video on the anti-science theory. So today I want us to quickly wrap up vertical projectile motion, and the very last thing that we will be covering on this topic is your graphs, right? So it's very important that you know all your different graphs. Make sure that you understand your graphs. You must be able to interpret. So there are very important things that you must be able to do with these graphs. So what's the first point? You must be able to identify the type of graph that you are given, right? You must be able to identify the graph. That is, regardless of the fact that you're given a, how can I say this? Regardless of whether the fact you're given a certain type of graph, without looking at the statement that tells you what type of graph it is, you must be able to identify the graph on your own, right? So you must be able to identify the graph you are looking at, right? You must be able to interpret your graph. So graph interpretation is very important. You must be able to interpret your graph. So we're going to speak about graph interpretation. So you must be able to identify your graph, you must be able to interpret your graph, and you must be able to, very important, draw your graph. In fact, not to, okay, let's just say it's drawing or sketching your graph. You must be able to do these things, right? So these are the very important things that you must make sure that you know how to do by the time you get into the exam room. So when you're looking at the graphs under vertical projectile motion, you must be able to identify the given graph before you read the statement that tells you what graph it is. You must be able to interpret that particular graph. You must be able to draw and sketch your respective graph. Right. So under VPM, we'll be focusing on only 3 graphs. So we'll be focusing on the 3 graphs that I'm about to name for you. So these are the 3 graphs that you are going to be focusing on for this topic. And just write types of graphs that you must make sure that you know. So these are the type of graphs that you must know. So the first one would be your typical velocity versus time graph. Your velocity versus time, or your velocity against time, right? And then your second one would be your position versus time graph, your position against time, position versus time. And then your last one would be your typical acceleration versus time graph, acceleration versus time. Okay. So these are the 3 graphs that you must know. So all these things that I said you must be able to do, these 3 things, graph identification, graph interpretation, and graph sketching or drawing, you must be able to do for each and every one of these graphs, for your velocity time, for your position time, and for your acceleration time graph. So these are very, very important. Now, just to quickly dive into the first one, so I want us to quickly focus on our first one, which is our velocity time graph. Velocity against time graph. Now, ladies and gentlemen, it is very important that when you get to your velocity time graph, let me make this, I don't know, I'm just one person who always wants everything to be straight. There we go. So in looking at your velocity time graph, you need to understand how the graph is drawn, how the graph actually looks like, right? So I'm going to start here. So for starters, we're going to use the equation from your equations of motion. Vf equals to Vi plus A delta T, right? So remember, from here, remember what I told you in the first lesson. This A is not just any A. This is your gravitational acceleration. This is something that you must know. This is a constant. This is your gravitational acceleration, and this is a constant 9.8 meters per second squared, right? Cool. I don't know why I wrote that, if I'm gonna erase it again. And then from here, what we're gonna do is that we're gonna assume that the initial velocity is 0. So what happens when we do that? We end up with something like this. So the final velocity becomes 0 plus A times delta T. That is, from here, I can then say the final velocity equals to A delta t. So now, I need you guys to understand something. I'm going to say something very important. So for starters, what you must know is that if a constant, say K, or let's say C for constant. If a constant is equal to the quotient of two non-constant, let's say A and B. So what do I mean? I'm saying that K is my constant, right? And A is my non-constant, meaning it's a value that can change, right? It can be any numerical value. Once again, B is also a non-constant, right? So check something. What I'm saying is that if a constant is equal to, so when I say something is a constant, I mean it doesn't change, right? So I say this is going to be C for our constant. If a constant is equal to the quotient means division, right? If a constant is equal to the quotient of two non-constants, then we say that those two non-constants, A and B, are directly proportional to each other. Directly proportional. Proportional. So what do I mean? So let's say, once again, I have C equals to A over B. So let's say the value of A, okay, let's say C is 12, right? So let's say C is our constant 12. Remember, if it's a constant, it does not change. Then I decide to say I'm going to make the value of A 6, and I'm going to make the value of B, let's see, I'm going to make the value of B 1 over 2. I'm going to make it a half, right? Remember, at the end of the day, I'm going to say 6 divided by a half must take me back to 12. So notice something, 6 divided by 12 by a half is going to take you back to 12. But once again, if I go and I say, once again, my constant is still 12, but now I change my 6 and I make it a 12, right? When I change my 6 and I make it a 12, what becomes my denominator? In order for me to get back to the left-hand side, I need to divide by a 1, right? So notice something. I moved from a 6 to a 12. What happens when I move from a 6 to a 12? Remember, I increase my number. And I also move from a half to 1. When I move from a half to 1, what happens? Once again, I increase my number. So that is why we say, notice how both my A and my B are increased, right? We both increase the two. And when one increases and the other increases, what do we say? We say that those two variables of, yes, in this particular case, A and B are basically directly proportional, because when A increases, B also increases, right? So it's a very important point. So in this case, I wanted to focus on something. So now that we've established that A and B are directly proportional, what does this mean? It means if I decide to make my A the subject of the formula, I'm going to have something like this. A will be equal to C times B. But at the end of the day, you must still remember that A is directly proportional to B, right? So notice how that applies in our equation right here. I'm going to have what? I'm going to have my velocity and my time. Remember that this is a non-constant. And once again, delta t is also a non-constant. However, the value of A is a constant. What's the value of A? A constant 9.8. So that one is a constant. So notice something. Just as I had my constant in my example over there, right? Sorry. Notice how I have a constant here. So take basically what you would notice is that V final goes with A, my constant A goes with C, and my delta T goes with B. So in this case, I have A, which is my final velocity, and B. Okay, let me do this. So I'm basically saying is that the final velocity goes with A, right? My A, my gravitational acceleration, goes with constant C. And then my delta T goes with my non-constant B. So basically they follow the same form. So what I'm trying to show you guys here is that in this case, right, we notice that the final velocity is basically directly proportional to your delta t. So that's what I'm trying to show you guys. And now notice something. Once you've noticed that your VF is directly proportional to your time, so we're just going to look at it this way. We are going to say, I'm going to have my Y equals to mx plus c. Notice how this takes the form of a linear function or a straight line graph, where in this case, my y becomes my velocity, my gradient becomes my a, my constant, right? And my x becomes my delta t, and obviously my c is going to be my 0. It's going to be my initial velocity of 0, right? And then notice something. When I draw my velocity versus time graph, how will I have it? So this is how I'm going to have my velocity time graph. Remember, it must follow the form of a linear function. So I'm going to have my Cartesian plane. So I'm going to have something like this right here. Okay, so that is my Cartesian plane. So from here on the Cartesian plane, I'm going to say, what exactly goes on my y-axis? It's my velocity, right? So I'm going to remove this part actually. I should have just started here and just drawn it all the way there. So on my y-axis, let me label my x's. So this is my y, this is my x. On the y-axis, I'm going to have my velocity, right? And then on my x, I'm going to have my, notice how they correspond, my delta t. So I'm going to have my delta t on this part. So this is in seconds and this is in meters per second. Right, and then what do you notice about the gradient? My gradient is the value of A. It is my gravitational acceleration. And in this particular case, my gradient is positive, right? So I'm going to have a graph like this. Remember that if you have a graph with a positive gradient, then you need to have something of this nature. And now I want you guys to understand something. In vertical projectile motion, when we say that when we say that the value of A is positive, if A is a positive 9.8 meters per second, what do we mean? We obviously mean that we took downwards as positive, because if A is always acting downwards, remember that A always acts downwards, and it has a positive value right there. That tells you that we took downwards as positive. So in this case, this graph would be the velocity time graph for when the value of A is a positive 9.8. That also means that you took your direction downwards as positive. So what am I trying to make you understand? Is that this particular velocity time graph, basically a velocity time graph with a positive gradient, tells you that you're looking at downwards as positive. Once again, a velocity time graph with a positive gradient, that is an increasing gradient like this one, this tells you that the value of A was positive. And if that's the case, then automatically you must know that that's when you have chosen your downwards motion as positive. Once again, if your gradient of your velocity time graph is increasing, that tells you that you have chosen downwards as positive. So let me write that on the side. Just a quick side note. We're going to call that our NB. So when the gradient of our velocity time graph, is increasing, in that case we mean that it's positive, then we say, what we can typically say is that, downwards motion was positive and automatically upward motion was negative. Right. I hope we are all clear in that department. I hope you guys are all on the same page. I hope none of you guys lost me, right? And then again, the same applies. If I have a Cartesian plane once again, right here, so I draw my Cartesian plane. And in this case, I'm going to have something like this. Once again, delta t is on our x-axis, and our velocity is on our y-axis, and that's in meters per second. If I have a graph like this, let's make it a straight line. If I have a graph like this, what does this tell you? This tells you that you have, for starters, a decreasing gradient, ladies and gentlemen. And if I have the form VF equals to A delta T, which is going to be Y equals to MX, what do you notice? You notice that my gradient once again, which is M, corresponds with A. So in this case, this means that I had a negative gradient, right? That means I had a negative M, and as a result, I have a negative A. So if your value of A is a negative 9.8, what does this tell you? You remember that when you have a negative 9.8, remember that this is negative 9.8 downwards, right? And I then said, I chose, if I have a negative A, that means I chose upwards as positive. Because once I choose upwards as positive, I know that anything downwards must be negative. Remember these things that we covered in the first two sessions. So in this case, what am I looking at? I'm looking at the fact that I have a negative gradient A. Remember that the gradient of my graph here is the value of A. And in this case, I have a negative 9.8. And if I have a negative 9.8, what does that tell you? It tells you that the downward motion was negative because A always moves downwards. And as a result, the upward motion was positive. Right. So these are very important points that you must remember. Once again, I'm going to have a side note here for you guys. So I'm going to write it down. I'm going to say my NB. When the value, okay, not the value, rather let's say when the gradient of the graph is negative, this means when the gradient of the graph is negative, this means that the value, when the gradient of the graph is negative, this means that upwards was positive, and as a result, downward becomes negative. So these are very important side notes that I really hope you guys can take as I'm writing it down. You also write it down in your notebook or on a piece of paper or something like that. So these are very important. Why are these important? So that by the time you get to an exam, when you see, let's say you're given a graph in the exam and you're asked to interpret the graph and answer the questions based on that graph. Just by looking at the graph and the gradient, given that it's a velocity time, when you're looking at a velocity time graph and you look at a gradient either increasing or decreasing, you must be able to tell that if it's increasing, the value of A was positive, and if the value of A is positive, that already tells you that downwards is positive, and as a result, upwards is negative. So once again, you get your exam, you get a graph with a velocity time graph with an increasing gradient. It's very important for you to tell that once I have a graph with an increasing gradient, right, I have a velocity time with an increasing gradient. What does that tell me? A velocity time graph with an increasing gradient tells me that downwards was positive, right? That's what I have in my side note here. Okay. Once again, you come to the second one. When you look at your velocity time graph and you notice, oh no, I have a gradient that is decreasing. So ladies and gentlemen, if I have a decreasing gradient in my exam, Given that I'm given a velocity time graph, and I notice that, oh no, my velocity time graph has a negative gradient. What does that tell you? You must remember that if my velocity time has a negative gradient, that basically means that my upward motion was positive. So these are very important points to remember. But how can you tell that your upward motion was positive? Remember that the value of A, the gravitational acceleration, is the gradient of your graph. So in that case, if the gravitational acceleration is the gradient of your graph, you will then decipher from there, or we'll see that from there you can then say that since the gradient of my graph is the gravitational acceleration and I have a negative gradient, that means I had a negative gravitational acceleration. And if your gravitational acceleration is negative, what does that tell you? That upward motion was positive. Right, I really hope you're all on the same page in that department. Cool. And then now I just want us to look at the next one, which would be your typical position time graph. So I'm just going to have that position time. Right. Position time graph. I really hope you guys followed me on my vertical on my velocity versus time graph. That's very important. We're going to do a couple of questions in the next video so that we can see how this works. Sorry. Okay, so I'm looking at my position time graph. So once again, you still need to apply the same logic. You must be able to identify the graph, you must be able to interpret your graph, and you must be able to draw or sketch your graph. So in this particular case, we're going to be looking at the equation delta y equals to the initial velocity times delta t plus 1 over 2 a delta t squared. So notice something. Once again, I'm going to assume that the initial velocity is 0. Right? So assume that the initial velocity is 0. That means we start from the point of origin, right? From the origin point. Let me show you guys what I mean. So here, notice something. I had assumed that my initial velocity was 0. And when we wrote this in terms of a linear function, remember we basically have 0 plus this, so this becomes plus my velocity initial, which was 0. So in this case, my value of c, which is my y-intercept, goes hand in hand with my initial velocity. Hence, on my graph started at the origin where the initial velocity is 0. Right. So once again, we do the same thing, and we're going to say, if the initial velocity is 0, what will I have? I'm going to have delta y equals to 1 over 2 a times delta t squared plus the initial delta t. But now I'm going to substitute my 0, so this becomes 1 over 2a delta t squared plus 0. Right, that's my delta y. And as a result, I end up with something like this. Delta y becomes 1 over 2a delta t squared. Notice something. What does this graph follow? Does it follow the linear function once again? No, not exactly. Let's see what it does. So we're going to have y equals to right, so this is y equals to ax squared, right? So what does the value of a basically tell us? So in this case, ladies and gentlemen, remember, on your typical quadratic function, you have y equals to ax squared plus bx plus c. So what a basically tells you, remember, it tells you about the concavity. Are you going to have a concave down, or are you going to have a concave up? Remember, if you have a concave down, that means the value of a was less than 0. That means the value of a was negative. And if you have the value of a greater than 0, then you have a concave up, a smiley face. That means the value of a was positive. So we're going to apply the same logic here. Notice something. In this particular case, my y becomes my delta y, and my a becomes my 1 over 2a and then my x squared becomes my delta t squared. So in this case, what I'm basically saying is that my x becomes my delta t if I square root both sides, right? So if I'm going to have my graph, I'm going to have something of this form, right? So we're going to follow a parabola. Remember, this follows the equation of a quadratic function. So I'm going to have it like this. I'm going to have my Cartesian plane once again. Okay, and then I'm going to have something like this. And then remember, the y-axis has, my delta y. Remember, we said that this is what we have. The y-axis follows your delta y, and your x-axis has your delta t in seconds, and then my delta y is in meters. And then now, ladies and gentlemen, I want you guys to focus on something. In this case, notice something. When you have the equation y equals to 1 over 2a plus delta t squared. Sorry, it's not plus, it's 1 over 2a delta t squared. What do you notice? You notice that the value of a, which is the one that determines the concavity, in this case, it was a positive value. Notice how there's a positive sign here, right? So if there's a positive sign, then you must expect a smiley face, right? You must have a graph that is concave up. So in that case, you're going to have something like this. So this would be your concave up graph, right? So that's how it would look. So this graph in an exam, if you see a graph like this, what you must know is that the value of A, your gravitational acceleration, was a positive 9.8. And if it's positive 9.8, what does that mean? Downwards was positive, right? And as a result, upwards was negative. So these are all the things that you must know, guys. These are very important points to remember. By the way, this graph will not always lie in the first quadrant. It can overlap into the second quadrant. It will depend on the question, but that will be very clearly explained once we do a question, right? And then again, I have another Cartesian plane. So I'm going to have a Cartesian plane like this. And then from here, I'll have something of this nature. So I'm going to keep it like this. And then I'm going to have my equation once again. So it was what? Delta y equals to, I don't know why I keep making it a very long x-axis. Right, so let's keep it there. I'm going to have my delta y equals to what? 1 over 2a delta t squared. Right, now, ladies and gentlemen, I want you guys to focus on something. So I'm going to have once again y equals to a, right, delta, sorry, ax squared. This is my x squared, right? Cool. And then notice something. If it happens that I have a graph like this, a concave down graph, what does my concave down graph basically tell me? Well, remember in grade 10, the first time you did function, you knew that when you have a concave down graph, that means the value of a was less than 0, meaning the value of a was negative. So how can I alter my delta y equation to be negative? I can then say this is delta y equals to 1 over 2 times a negative 9.8 delta t squared, meaning the value of my gravitational acceleration was negative. I'm then going to have something like this. If the value of my gravitational acceleration is a negative 9.8, then I know that my upward motion was positive. And automatically the downward motion becomes negative, right? So these are very important things that you must know. So how do you get to understand what goes on in the exam? So you get to an exam and you get a graph of position versus time that has a positive, a concave up shape, right? If you have a concave up shape, what is important for you to remember? Once you have a concave up shape, you must remember that the value of A is positive. Your gravitational acceleration was positive. So let me have a side note once again. So if you have a concave up graph, what you must remember for yourself, please have these side notes for yourself when you study. You're going to then say, if I have a concave up graph, what does this tell me? The value of my gravitational acceleration that is the value A, was positive, right? And what do you know about the gravitational acceleration being positive? This means, what does this mean? Aha, this means that upwards was positive. Oh, no, I'm lying. This means that downwards was positive, right? So please have your notes on your book. This means that downwards was positive, and as a result, upwards must be negative. Right. And then another side note on this side as well. So for this one, we're going to say, if it happens, right? So this is your side note, your NB. Let's make it our NB. If I know that when my graph is concave down, then that means the value of A, the value of my gravitational acceleration, was, when my graph is concave down, then that means the value of my gravitational acceleration was negative. Meaning, if the gravitational acceleration is negative, what does that mean? Yes, it means that upwards was positive, and as a result, downwards is negative. Right, so ladies and gentlemen, these are very important. How so? How else are these important? Let's say in the graph, in a question, you are required to draw. Instead of interpreting, you are required to draw the graph. You must remember that when you are required to draw the graph, you must remember from the direction you chose. Remember, you must stick to your initial direction from the beginning until the end of the question. From the direction you chose, if you chose upwards as positive, then you know that you must have a velocity time graph that looks like this, that is concave down, if you chose upwards as positive. If you have, once again, if you chose upwards as positive, then your position time graph must be concave down. And then if you chose upwards as positive, once again, your velocity time graph must have a decreasing gradient, right? If you have chosen downwards as positive, what does that mean? Your velocity time graph must have a increasing gradient, right? And if you have chosen downwards as positive, then your position time graph must have a concave up face, or shape rather. And there you have it. So ladies and gentlemen, this is very important. It's very important for you to understand these. But for now, I shall end this video here, and we will see each other in the next video where we'll be doing past questions on vertical projectile motion graphs, and then we can then conclude the topic. But from me to you now, please don't forget to like, comment, and share with your friends and family and anyone that you really feel like would actually benefit from this content. Please don't forget to share with them, and I will see you guys in the next video. Goodbye.